So the next thing which comes is the illustration. We have discussed what exactly we mean by the different type of reasoning which is called as induction reasoning. So if we wish to find the formula of say, or for the sum of some positive integers, say 1 to n, what will be the formula? And if n equal to 3, it will be say 1 plus 2 plus 3, because these are three terms. If you say n equal to 4, there will be 4 terms, as you can see here, 1 2 plus 3 plus 4. And now just imagine that you want that you want to believe, or you want to assume, or you want to tell somebody that okay, 1 plus 2 plus 3 till n is nothing but n plus 1 by 2. Is it correct? How you're going to prove it? How the other person is going to believe it that this type of formula is correct? So how to prove? The basic thing is for to n to hold for all these values is, we'll call something which we just discussed, is called the chain reaction. Chain reaction means if you're talking about some n value, you are saying okay, let us start and say okay, it is true for 1. Let us assume midway, okay, it is true for say some kth value, and we found by some mathematical assumption calculation that it is true for k plus 1 also. So for every k plus 1 it will be true for k plus 2, and likewise. So there will be an induction effect till 1. So you start with 1 and you reach at n. So this is the principle of mathematical induction, which we are going to see formally now. Suppose there is certain given statement, we call it as Pn. So every statement which we are going to prove, we will call it as Pn. But why Pn? Because this is the statement, and n, it involves certain natural number, that is n. So the statement first is, this is the basic step we call it, that the statement is true for n equal to 1. That means for any equation we are going to put n equal to 1, and we see that P1 is true or false. Second step is, if the statement is true for say any number, you take n equal to k in between or wherever, where this k has to be some positive integer, then the statement is also true for n is equal to k plus 1. If it is true for n is equal to k, you are saying it to be true for n is equal to k plus 1. So the truth of pk actually implies in the truth of pk plus 1. If you can ever get it that pk is true, pk plus 1 is also true, then you say that the principle of mathematical induction has worked. So Pn is true for now all natural numbers if these two conditions are met. This first property is actually the statement of fact, that okay, it is going to happen for this. So let us start, and if in the first verification step we say it worked for 1, okay, now it is good, let us go ahead. And the second property, this is known as conditional property. Why it is conditional property? Because it is not going to assert that the given statement is true for n equal to k. You are actually feeling, and you are actually assuming that it is true for n equal to k. You are not saying that it is n equal to proved till now that it is n equal to k. You are assuming it to be equal to n equal to k. It is true for n equal to k, but when the k increment or it increases by 1, this also holds true. If you can anyhow do this, if it can be proven, the property holds. And the proving is called the conditional proposition. That is, if the statement is true for n equal to k, then it is also true for n is equal to k plus 1. This also is sometimes referred to as a step called inductive step. And the assumption that the given statement is true for n equal to k, as we have just seen, is the inductive step, which we call it as inductive hypothesis. For instance, in mathematics, there is a pattern. Say, just try to find out how it actually goes. So 1 is what? 1 square, 4 is 2 square, 9 is 3 square, and 16 is 4 square. So 1 is nothing but 1. 4 can be written as 1 plus 3. 9 can be written as 1 plus 3 plus 5. 16 can be written as 1, 3, 5, 7. So what we have got here is worth noting that the sum of first two odd natural number is the square of the second natural number. So first sum of the first three, this one odd natural number is the square of the third natural number, and so on. So this pattern can be written as in the expression form as 1 plus 3 plus 5 plus 7, and this 2n minus 1 is nothing but a representation for an odd number. This is equal to n square. So the sum of first n odd natural number is equal to the square of n. So let us start our mathematical induction that Pn is equal to what we have been given. So you want to prove this Pn is true for any n you can assume. So the first step in this proof, it uses the mathematical induction, that is P1, which has to be true. So this is obviously true. Why? Because 2n minus 1, you place 1 here, you place 1 here, both sides you will get 1. So the basic step is done. 1 is equal to 1 square. Now, the next step, we call it as inductive step. We assume and we suppose that pk is true for some positive integer k, and we now want to prove that pk plus 1 is true. This is what you have to do for every question. And since pk is true, we assume that, or we know that, okay, this is true. 1 plus 3 plus 5 plus 7 plus say 2kn minus 1 is equal to k square. This we assume to be true. Now just consider, because we are now going to k plus 1. So we are adding the k plus 1 term. So we are placing k plus 1 in place of k, adding this and then plus of 2k plus 1 minus 1. That is, we have added the k plus 1th term. Here also we will add k plus 1th term, that is k plus 1 square. Okay. So what you get here, this you have already known. What this left hand side part is already k square by 1, and this you have added. So ultimately you are adding this. So what it gives is k plus 1 whole square. And this is what we wanted to know, because if it is true for k, for any k plus 1, it gives you k plus 1 whole square. For k, it gave you k square. For k plus 1, it gave you k plus 1 whole square. So pk1 is true and the inductive proof is completed. So now you can state or assert that Pn is true for all natural numbers n. So now we have seen what mathematical induction exactly is. Next is we are going to take this question. Till then, thank you so much. Take care of yourself.